Okay, so here we've got our mass on a spring, just like in the word problems. And just like we expected, we perturb the spring and it oscillates up and down. Now that we've done those problems, we see that oscillation means trig, which means complex conjugate eigenvalues. Let's think about the x and the y, the way that we were measuring distance. Originally, when we first set up the model, we were measuring distance from, this would be y equals 0, from the unstretched spring. But if we measure x, then that's from the equilibrium position. This would be x equals 0. So the distance from here to here, so this distance that's the equilibrium distance. That's the coordinate shift that we do to change the y coordinates, where we had a linear second order constant coefficient non-homogeneous differential equation. When we did that coordinate shift, we end up with a linear constant coefficient homogeneous differential equation when we measure from here as the x equals to 0. Made for an easy equation. Both the homogeneous and the non-homogeneous, of course, had the same auxiliary equation, so they had the same eigenvalues. So what we've got here, I didn't build this rig. This is borrowed from Professor Olis lent me this. She's got this in her office. So I've got these springs, these masses oscillating on springs. And what the things that we can do here? Well, we can do a live action word problem, I guess. But one of the things I want to talk about is if we know what the equilibrium value is, because I know this distance, if I know what the equilibrium value is, then I can figure out the K value. I can figure out the spring constant. Remember, in our problems, there's three positive constants. There's the mass. We'll just have to weigh that mass and get how many kilograms it is. The spring constant we can get by measuring the equilibrium distance. And then the only thing then I need left over is the C, or the coefficient of friction. So to get the coefficient of friction, I can measure the period, and I know that the period, 2 pi divided by the period is 2 pi divided by the imaginary part of the eigenvalue. So if I can measure the period in seconds, then I would know that that's 2 pi divided by the imaginary part of the eigenvalue. So I could figure out what the imaginary part of the eigenvalue is, and I already know at this point m, because I weighed this, and k, because I measured that. So then I can solve for c. I can get all of the three positive constants. Now, why there's three systems here is we're trying to illustrate the different dampness. This one oscillates back and forth. It eventually dies down. What do I see when we see this? Well, we have oscillation. So there must be complex conjugate eigenvalues. So there's trig involved here. The negative part of the eigenvalue is real. This is working like we think a spring should work. This is underdamped. If I go all the way over to here, where this is 10W30 motor oil, and if I perturb this, there's no oscillation. It just goes back to equilibrium. So this one is dirty. Overdamped. The friction is there's so much friction that it doesn't oscillate like this underdamped. So this is real and different eigenvalues, both negative. This is complex conjugate eigenvalues, real part negative. And this one in the middle, as you'd expect, this one's going to be critically damped. So this one in the middle, critically damped, the eigenvalues should be real and the same. The thing under the square root sign should be exactly 0. Thing under the square root sign here negative, thing under the square root sign here positive, talking about the eigenvalues. Here the thing under the square root sign should be 0. This one should, is a sort of the knife edge intermediate case between underdamped and overdamped. This one's critically damped. So the eigenvalues should be real and the same. I shouldn't be able to tell the difference between these two if I were to graph it.
Science, bitches.
Oh, so What else do we got? We got the M, we got the C, we got the K that we measured. The only other thing is if there's a forcing function, an outside force, that would be this thing is oscillating and I'm like doing something to it. This is the outside forcing function, the G of T, me poking it with a stick or my finger. So we have underdamped, critically damped, overdamped. How does that sit with you? Okay, I'm done.